what happens when a comet crashes into a planet? In July of 1994, it really happened when around 21 to 2 kilometer sized fragments of comet Shoemaker-Levy 9 plunged into Jupiter. Despite Jupiter's huge size, the relatively tiny comet fragments made a spectacular impact, leaving huge scars thousands of kilometers across.
This crater was the first meteorite crater in the world that was shown to be a meteorite crater. So it was extremely important in that first intellectual step to recognize that, yes, indeed, very large objects do fall out of the sky and make holes in the ground.
The object that formed Meteor Crater in Arizona 50,000 years ago was a relatively small one, around 60 meters in diameter. Nevertheless, it left behind a crater more than 1 kilometer across and 200 meters deep. Had just one of the Shoemaker-Levy fragments hit the Earth, it would have had a destructive force of more than 20,000 megatons of explosive and would have produced a crater 20 kilometers wide. In common with the other planets of the solar system, the Earth has been hit by asteroids or comets many times. On Earth, we see very few craters because geological processes such as weathering and erosion soon destroy the obvious evidence. As a result, the idea that rocks the size of mountains can fall from the sky and affect life on Earth was often viewed as heresy by geologists. But craters do exist on Earth, though finding them can take you to some surprising places. One such place is the top of St. Georg's Church in the town of Nördlingen in southern Germany, which is situated close to the center of the Ries crater.
Well, that was some climb. As I've walked around the tower, then everywhere on the horizon I can see a single topographic expression of the crater, and that's the crater rim.
Although it's one of the best preserved impact craters on Earth, all we can see of the rim today is a ring of tree-covered hills in the distance that outline the 25-kilometer wide crater. The asteroid that formed the Ries crater was more than 1 kilometer in diameter, roughly the same size as the walled town of Nördlingen. St. Georg's Church bears witness to this cosmic event, as it's built from a rock called swavite, which was formed as a result of the impact. Yet for hundreds of years, the inhabitants of Nördlingen had no idea that they were living on the site of a catastrophe of truly cosmic proportions.
The Romans used a swavite here for building purposes. In 1805 or so, we had the first scientific description of the Ries crater here. So, for example, Fluel or von Gümbel, they were the old geologists here in Bavaria.
By the time we get a map, the 1848, we're actually seeing the rocks described as volcanic.
Yeah, that's right. This is the oldest mapping of the Ries geology, coming from 1848. Now the geologists who produced the map found a circular structure of almost 25 kilometers in diameter and explained it as a volcanic crater.
So when did the impact idea first surface?
1904. There was a scientist, Werner. He first described the Ries crater as an impact structure.
And did anybody believe him?
Nobody.
Nobody.
It's the same happened a couple of decades later with Schuster, who did the same. He picked up this idea, but he it was the same fate for him. Nobody believed him.
So when did an impact really become the settled argument for the origin of the Reese crater?
Well, an important event was in 1960, when Eugene Shoemaker, famous geologist, visited the Reese crater, and he came to the quarry of Otting, where he picked up a suite specimen.
What Shoemaker and his colleague Ed Chow had found was conclusive evidence that the swavite is indeed the product of an impact.
When we examine these rocks, we can see that they're composed of various fragments. These fragments are pieces of the crystalline basement that underlie the crater.
When Chow and Shoemaker looked at the rocks, they found that the quartz crystals within them had undergone several changes. The atoms slip and reform in layers as a result of the impact. We see the lines between these layers. Other crystals had their structures altered with the high temperatures and pressures to produce two new minerals, stishovite and coesite.
Glass. We all know it's a product of melting at high temperatures as minerals are fused together and then cooled. It shouldn't surprise us, therefore, that we find glasses in the swavite.
These dark glasses can be up to several tens of centimeters in size. They're made during the impact, when the target rocks are subjected to such high temperatures that they're fused together and then quenched as the impact's fireball cools. The glasses also contain bubbles as a result of the sudden and rapid degassing that occurs as the rock is heated. The asteroid that formed the Reese crater had a destructive force equivalent to nearly 20,000 megatons of explosive. Nuclear explosions are one way of reproducing the high pressures and temperatures that occur during an impact. Fortunately, there are some safer experiments that enable us to model impact processes. In the late 1980s, Peter Schultz, working at the NASA Ames Research Center, used a compressed air gun to accelerate a projectile to several kilometers per second to study the formation of craters. The whole process lasts less than a second, so high-speed cameras are used to record the action.
That's great. Okay, that did just what we expected. Here we can see where the red temper that we had on the surface of the target has been covered by the lighter material that was below it. And you can see the decay, and eventually that of the thickness of that ejecta, and eventually it gives out about here, where it predominantly becomes red. And as you go farther out, you can see just primarily red clumps that have impacted.
By slowing down the impact to 1/16 of normal speed, we can see the curtain of ejecta that forms as the projectile hits the target. From such experiments, we can reconstruct the Reese impact. The asteroid crosses the Earth's atmosphere and becomes a brilliant fireball. At a speed of more than 35,000 kilometers per hour, this cosmic bullet penetrates the Earth's surface and comes to rest at a depth of approximately 1 kilometer. As a highly compressed gaseous body, it explodes and a shockwave spreads from the base of the crater. Molten, vaporized and pulverized rock is then ejected. In less than 1/10 of a second, this has reached its climax. During the next minute or so, a red-hot mixture of solid, liquid and gaseous material forms a blazing cloud over the crater. The high temperatures at the center of the crater cavity melt large amounts of the target rock. These fragments of green glass have the same chemical composition as the Jurassic and Triassic sandstones in the Reese. They were found in Moldavia in the Czech Republic, over 400 kilometers from the crater. Not surprisingly, they're known as moldavites.